Hello. In this video I'm going to show you how I start my T62 T-32 gas turbine engine in my Helicycle N750 Golf. But if you're like me, you want to know why I'm doing what I'm doing. So I'm going to spend quite a bit of time going through the engine and how the thing operates and what all the various components do. But eventually I will get to a video and actually start the engine. So bear with me, I'll get to it. Here's a view of the engine as viewed from the right side as it's installed in my Helicycle. I'll go through some of the major components quickly. In the upper right is a 55 amp alternator, which is unique to my helicopter. I wanted a lot more electrical capacity than the standard unit. The large gray tank below and to the left holds a couple quarts of synthetic aircraft turbine oil, which is used to lubricate the engine. The engine has a dry sump, so there's an engine-driven oil pump, and there are two engine-driven scavenger pumps that pull oil out of the engine, out of the transfer case, and put it back into that tank. Directly below the red master switch is the electric starter motor. To the right of the starter motor is the gear reduction and accessory drive assembly. That unit is where the starter motor mounts. It also provides drive to the fuel and oil pumps and drive to the large 6-sheaved pulley that you see in the lower right portion of the engine below the oil tank in this picture. The 6 drive belts then drive another pulley which is attached to the input to the main rotor transmission, and they also drive the tail rotor drive shaft, and that drives the gearbox and tail rotor. The screen below the starter extends all the way around the engine. That's the air intake. To the left of the starter is the combustor housing assembly, and to the left of that is the engine's tailpipe. Here's a closer view of the starter and its attachment to the gear reduction drive. That unit, incidentally, is custom made by Eagle R&D for the Helicycle, so it's not a standard part of the military surplus gas turbine engine. That's unique to the Helicycle. Now, during a start, the starter motor draws 1200 amps initially, dropping to about 450 amps after a few seconds. That huge current surge causes the battery terminal voltage to sag to about 8 volts momentarily, and that's not good for any of the equipment that's trying to operate during an engine start. The valves and the solenoids, the igniter, all of the instrumentation, they all have problems trying to operate at 8 volts. They're not designed for it. So what I do is I have an isolated power source that's cutting in during the start, and my DC bus is switched off of the battery to that isolated source of power, and that prevents that 8 volt sag from getting to any of the equipment. Here's a graph in which the magenta curve is looking at battery terminal voltage during an actual start. And you can see initially the voltage was about 13.3 volts. As soon as the starter was engaged, within a few seconds that had dropped down to just slightly over 8 volts. And then as the starter begins to turn the turbine, the load is reduced on the starter, and the current is decreased from 1200 amps to about 450. The battery voltage then rises to about 8.5 volts, which is still way too low for proper operation of any of the electrical or electronics equipment on the helicopter. The blue line is my isolated DC bus during a start, and you can see that it is very stable. So I've got a good source of electrical power during a start, which most helicycles don't have. That's one of the things that I worked on as an enhancement on my helicopter. Let's take a look at the hot section. This portion is called the combustor housing assembly. Air is drawn in through the screen intake that I showed you a while ago, where it's mixed with fuel and ignited. Now let's take a look and see how that works. As I mentioned, the starter motor spins the compressor up. Air is drawn in through the inlet, forced into the combustor, where an aerosol spray is squirted from the start fuel nozzle, and that combustible air fuel mixture is then ignited right here. The igniter spark plug that I'm pointing to goes snap, snap, snap. It puts out a spark about once a second, and once the flame is lit, then the igniter is turned off and the flame is self-sustaining after that point. Now once the engine is lit, open the master fuel solenoid, which allows high pressure fuel to pass from the fuel control unit back to the 6 nozzles in the back, 3 of which are visible on the right side and 3 more on the left side. That fuel then is mixed with the air fuel mixture that's already burning, and that produces even more hot gas, which then spins the turbine wheel, and you'll see in a second how that all works. Okay, this is the only part that actually moves, the only large part that moves inside the engine, and it's called the turbine rotor assembly. On the left side is the compressor. On the right side is the turbine. The whole thing is mounted on one shaft and turns as a unit. Now let's take a look and see how that fits into the engine. So here's a cross-sectional view of the engine. Right in the middle there is that assembly, with the left side being the compressor, the right side being the turbine. If you look at the blue line, you can see cold air being drawn in through the inlet by the compressor. It's then forced around, if you follow the blue line, right along the top of the combustion portion of the combustor and right against the skin of that assembly. And so that cooling air helps keep everything from melting. The air then bends around again and heads back into the combustion area where the nozzles are spraying fuel, and it's lit on fire in there, and that's represented by the red line. It then exits through the turbine blades and exits out the back of the tailpipe. So as that hot gas spins up the turbine blade, it's on the same shaft with the compressor. The compressor speeds up and brings more fresh air into the engine, and that's the circular flow of the engine. More cool air is brought in, fuel is mixed with it, hot air comes out the back, spins up that assembly, and away we go. Now that whole operation is controlled by an electronic governor, which is inside the box that I've marked out in red. The governor controls the speed of the engine by regulating the amount of fuel that is supplied to the engine. And it's housed in that cast aluminum box to prevent interference from, mainly from the radio in the helicopter. That's called electromagnetic interference, or EMI. So protecting against that is critical. We don't want any malfunctions because the engine could shut down in flight. And so the electronics inside that box is shielded by the box. All of the input and output lines are also shielded, and they're also filtered against electromagnetic interference. The electronic controller then controls the torque motor, that round assembly on the right side of the area that I've marked off. That whole area marked in red is called the fuel control unit. The way that works is the torque motor on the right is controlled by the electronic governor. You can see a shaft protruding from the bottom of the torque motor, which is connected via some linkage and held in the idle position by a spring over on the left hand side. And as the torque motor exerts more force against the force of the spring, the shaft in the middle is rotated, and that turns a shaft inside the fuel control unit. That shaft then helps control the amount of fuel going to the engine. There's also another input from a barometric sensor that's mixed in with the position of that shaft to ultimately determine how much fuel is supplied to the engine. Now, the electronic governor itself has two inputs. I've just talked about its output. The two inputs, the first one is the throttle twist grip, which is at the left side of the collective that you see here in this picture. Via a shaft running down the inside of the collective, there is a precision potentiometer at the other end, so that the resistance varies as that twist grip is rotated. That varying resistance is sent up to the electronic controller, and that's the command that tells the controller what RPM I'm requesting. The other input is shown here. It's a magnetic pickup that sends out a string of pulses which vary in frequency with the RPM of the engine. And so the twist grip tells the controller what I expect out of the engine, and this magnetic pickup tells the controller what the engine in fact is doing. The controller itself is a servo system, so it's simply looking at those two inputs, and if there's a difference, then it tries to close that difference by either increasing or decreasing the amount of fuel flow to the engine. Now, during start and in flight, I'm looking at the instruments that I've outlined here in red, as well as the one up in the upper right that's partially in the picture, to tell me if the engine is operating correctly. So I'll go over those one by one. Now, the first one is the fuel flow indicator that reads out in gallons per hour. That one is actually not used during an engine start, but I monitor that fairly closely in flight. At full power, the engine consumes 17.5 gallons of jet fuel per hour at its rated output of 150 horsepower. But the engine in the helicopter is only loafing along at 80 or 90 horsepower and typically consumes around 13.5 gallons per hour, which is in the middle of the green band. So you can see from that that the engine has a tremendous amount of excess capacity. It is not working very hard at all in the helicycle. Another good thing about this fuel flow indicator is it's a fairly good indication of the amount of horsepower that I'm supplying to the rotor system. And I will be getting light on the skids during takeoff right around 13 gallons per hour. So as I'm pulling back on the collective, I can watch the fuel flow indicator initially to monitor my progress and determine when I'm going to start getting light on the skids. When I get up around 12 gallons per hour, I'm going to shift my focus from the instruments to looking outside the helicopter to judge my attitude as I'm getting light on the skids and getting ready to lift off. The next indicator is a dual indicator, engine oil temperature and oil pressure. During engine start, I'm not concerned with oil temperature because that's going to take a while to come up off the peg. But I do monitor oil pressure very carefully. the oil pressure should pop right up into the green before the engine is even started. Just spinning it up on the starter motor it will get things going enough to get the oil pressure up and oil, lubricating oil flowing through the engine, and that's critically important. The next thing I'm monitoring is EGT, or exhaust gas temperature. I want to make sure that it does not spike up into the red. If it does, that calls for an immediate engine shutdown. That's something called a hot start. So I watch that as well. And lastly, the other indicator that I keep an eye on is this dual tachometer. The needle in front with the R on it is rotor RPM, and during a start that's just going to stay at 0 because the clutch is disengaged, so the rotor system will not be turning. Underneath it, hidden from view, is another needle with an E on it. That's engine RPM. And there's three critical things that I look at during the start. The red mark at 30%, which is time to turn the starter off. The 50% mark, turn off start fuel goes off, and then the yellow band between 75 and 80%, which is idle. So during a start, I'll be watching that, and that will determine when I let off of the starter and the start fuel. And I'll show you that in a little while. The last thing to mention are the various switches here on the lower instrument panel. The ones on the top row, I turn those all on before I start the engine. From left to right, that's the electronic governor that I mentioned. The electric boost pump. The middle one stays off. That's the master fuel solenoid. I turn that on once the engine is lit, and I hear that poof sound. Next is the alternator, and finally instruments. I can turn those on at any point before I leave. I could leave those off until the engine started and then turn them on. I normally just turn them on right away. Over on the left is avionics. That can be on or off during a start. It doesn't matter. The two in the lower right, the red guarded switches, energize the clutch and the starter circuit. Those are controlled by buttons on the cyclic grip. And so I flip those up, turn the switches on to energize those circuits, then I start the engine and engage the clutch with the buttons on the cyclic grip. Once the clutch is engaged, the engine's running, I flip those down, which turns those circuits off, de-energizes them. So if I accidentally push either one of those buttons in flight, it won't have any effect at all. So now, there's a few steps I go through before I actually start the engine. I just go through these very quickly. Turn on the master DC power switch. That was that red switch that I showed you way back at the beginning. Then I get into the helicopter and strap myself in. Look around, check to make sure the area is clear around the aircraft. Position the collective at the top of the seat pan, which is where I want it. It's more or less a zero pitch or a slight positive pitch, but not enough to lift off. Set the throttle to flight idle. I turn on my master fuel valve, which is under my left leg. Turn on the electric boost pump, then the governor, the alternator, the instruments. Both red guarded switches come on and up to energize the start and clutch circuits up to the cyclic grip. Make sure the clutch is disengaged. You turn on the strobe lights to warn people to stay away. Double check fuel quantity to make sure I have enough for the flight, and then I'm ready. So now we're finally to the actual start sequence, which I'm going to show you in a video on the next slide. So again, I'll be watching exhaust gas temperature, oil pressure, and the tachometer. I'm not really concerned with fuel flow during a start, so I'm only watching these three indicators. So I'll engage the starter. Within a second or two, it will spin up the turbine enough to start pulling air through the engine. As soon as I've got airflow going through there, Then I'll engage the start fuel and the igniter with a button on my cyclic grip. I'll listen for that poof sound of the engine lighting off. As soon as I hear that, then I turn on the master fuel solenoid, which is going to send fuel through all 6 of these fuel nozzles in the back of the engine that I showed you. And then the engine will start accelerating. It's still being accelerated not only by gas flow through the engine, but also by the starter. During this whole process, I'm watching to make sure all the indications are in the green. When I get to that first red line at 30% RPM, I'll release the starter. At that point, the engine should continue to accelerate. If it doesn't, then I'll stop the sequence and shut down. But that's never happened, so it will continue up to 50% RPM. At that point, I let off the start fuel. That closes off fuel to that start fuel nozzle, which got everything going in the first place. And then the line to that nozzle is actually purged of fuel. And you may hear the engine sort of surge at that point. That's that purged fuel being squirted in there. Now the engine's self-sustaining. I've let off of the starter and the start fuel, and it will simply accelerate up to flight idle, and it will stay there. And so now, finally, after this big long explanation, we're actually ready to go ahead and start the engine. Okay, here we go. I've already set the master fuel valve is on. Now I'm going to turn on the power. You're going to see instruments boot up. You're going to hear a large beep come out of my rotor alarm warning, and then everything will be booted up, ready to go. Okay, everything's booted up. We're all set to go. I'm not going to engage the clutch, so I'll leave that down. And we're ready to start the engine. So I'll hit the starter, then the start fuel. As soon as I hear the poof, I'll come on with the master fuel solenoid, and we'll be on our way. Here we go. And there you go. There was an engine start and an engine shutdown. When I shut it down, I never mentioned this before because I wasn't going to go into it. Once the engine's back down to flight idle and the clutch is disengaged, then I turn off the governor. And what that does is the spring that I mentioned on that linkage then pulls the throttle linkage back to the idle stop on the fuel control. So instead of the idle being controlled by the electronic governor, which is up in the middle of the yellow, it will slowly decelerate down to the actual idle hard stop, the mechanical stop. Once it's down to the stop, then they shut the engine down. And that's how that works. That's that. Well, I hope that was informative and not too long. As you can see, I could have actually made this into a 5-second presentation instead of 20 minutes or however long this took. In real time, as you saw, it's starter on, start fuel on, poof, hit the master fuel solenoid, starts to accelerate. 20%, 30% let off of the starter, 40%, 50% let off of the start fuel, accelerates up to idle, you're done. It's lit off, it's sitting at idle. That's about how long that takes. But there's a lot in the background that goes into that, so I hope that this explanation was of some use to guys who are building their helicycles and haven't got the engine started yet. Incidentally, I don't advise you trying this on your own until the check pilot gets out there to make sure everything's hooked up right. You can overspeed the engine faster than you can possibly react, so be very careful and don't get antsy. And to anybody that's thinking of building a helicycle, I think it's the best kit out there. It's a great joy to work on. It kept me happy for 4 years of construction and another year so far of flying it. So thanks again for watching.